Hello, everyone. This is physics lab number three, the mass of a black hole. Um, and this lab, we're going to be going over the mass of a black hole. Our table of contents include the key ideas, relevant formulas, the loop and video for code, the code and video for loop one, the code and video for loop two, and then the two essential questions of what does it mean and the what if question. Now, the key ideas of this lab are going to be Newton's second law of motion and momentum principle, as well as the product rule for differentiation, and also Newton's universal law of gravitation. Now, the purpose of this lab is for us to calculate the mass of the black hole. We're going to be doing that with the first loop, and then to find the initial speed of the rocket ship with loop two. So the relevant formulas we'll be using are F net equals dp/dt. We know we can rearrange and manipulate that formula in order to find the parallel and perpendicular components of it. We can see this represented by the arrows with this little diagram down here with the planet. The red arrow is going to be the perpendicular component, whereas the blue arrow is going to be the parallel component. We also know that F net, the only force acting on the star, is going to be the gravitational, meaning F net equals gravitational. And we know that gravitational is also going to be equal to dp/dt because F net is equal to both of those things. Now, we can rearrange the dp/dt and the gravitational formula in order to solve for M2, which is going to be our mass of the black hole. And you can see down here, in the end, I end up finding that the mass of the black hole was 9.7-ish to the 10 to the 33, and the initial ship speed was -6 e to the 7 in the x direction and 0.15 e to the 7 in the y direction. Now, for the first loop of code, we started off using the information that we knew. The star and the black hole were the system, with everything else being the surroundings. And so we set up everything we knew, like the time, we knew the mass of the star, the gravitational constant. And then down here for our V initial and everything, this is going to be the code that establishes the velocity and the momentum. And then for the F net equals dp/dt, this is going to be getting the F net as well as finding the parallel and the perpendicular components down here. And then eventually we're able to get the mass of the black hole using the universal gravitational formula right there. And then a video of the first loop is going to be right here. As you see, we have the three different arrows are parallel, the blue, the perpendicular, the purple, and the F net being the orange. And through these different calculations as it goes around, we get our final mass. Next, for the second loop, we use the black hole mass, which was determined from part one, as well as the initial conditions for the system and the universe plugged in. The surroundings are just going to be everything else, not really factored. Then we're going to use the initial speed to be the tangent to the black hole while still escaping. And this was found through a lot of trial and error process. And then we plug more code in that helps us to get the relevant position vectors or magnitudes, different directions, and calculate the solo gravitational interactions. And the solo gravitational interactions are summed to get the total of the gravitational forces. Then over here, we're going to be applying the position and velocity update equations to simulate the planet's motion. And finally, we're going to create the conditions for the ship to escape or to fail. That way we don't go that far. And then here's a video of that taking place. Fast forward a little bit. We can see that it gets very close around the edge of the black hole, and then it narrowly escapes while being within its gravitational effect. Now, to answer the questions, what does it mean? We know that the net force, the parallel perpendicular components are different from the rate of change of momentum, because the rate of change of momentum is going to be the momentum over time. Using the momentum over time, we can calculate a lot of different formulas to help us find all the forces acting on the planet. And then finally, for the what if, I attempted to do this but was not successful. I tried plugging in a bunch of different numbers, but I could not figure it out.